Welcome to our explainer for Lecture 13. As the internet exploded in popularity, we ran into a huge problem. Our traditional databases just couldn't keep up. So today, we're going to unpack the revolutionary cloud computing solutions that were invented to handle data at a truly internet-wide scale. All right, so here's our game plan. First, we're going to see why traditional databases just hit a wall. Then, we'll look at the new architectural blueprints that let us smash right through it. From there, we'll explore the new foundations and structures that got built, and wrap up by looking at the really tough design choices that every modern system has to make. Okay, first things first. To really get why these new systems were so revolutionary, we have to understand the problem they were built to solve. Why did the old way of doing things just stop working? It all boils down to the basic design, the fundamental limits of traditional databases. For decades, the answer to needing more power was simple: scale up. You just buy a bigger, more powerful, and way more expensive server. But there's a problem, right? You eventually hit a hard physical limit. You can't just make a server infinitely powerful. And besides the crazy costs, you create this massive single point of failure. If that one giant machine goes down, well, your entire application is toast. So here's the real kicker. The core issue was that these traditional relational databases, they were just built for a different world. They were designed for that scale-up model, where everything shares memory and disks. They were a total mismatch for the cloud's scale-out approach, which is all about spreading the work across thousands of cheap, independent machines. So if scaling up is a dead end, how in the world do you build something that can scale out, like to infinity? Well, it starts with a complete rethink of the basics, the architectural blueprints of how these machines actually talk to each other. And this table here tells the whole story. It's a perfect evolution. We started with this shared memory idea, where everything is fighting over the memory bus. That's your first bottleneck. Then came shared disk, which was a bit better, but then the storage system itself becomes the choke point. The real game changer was shared nothing. By making every node totally independent, you get rid of those bottlenecks. The only thing they share is the network, and that, of course, becomes the new resource you have to manage.
And this idea, this shared nothing architecture, it's everything. It is the absolute foundation of all modern distributed computing. Think about it, because every single node is its own self-contained unit. You can scale almost perfectly linearly. Need more horsepower? Just throw more machines at the problem. This is literally the key that unlocked the door to building systems on a scale nobody had ever seen before.
All right, so now that we have this shared nothing blueprint, we need a new kind of foundation to build on. You need a file system that's designed from day one for this new world of scattered, unreliable commodity hardware. And this is where the legendary Google File System, or GFS, steps onto the scene. What made it so revolutionary was this core assumption, which sounds kind of crazy at first: hardware will fail. It treated component failure as just a normal, everyday event, not some rare catastrophe. The whole system was built to expect and automatically handle constant failures, mostly by making copies of everything. This diagram shows the model perfectly, and it's brilliant in its simplicity. You've got this one master server that acts like a library's card catalog. It doesn't hold any of the books, but it knows exactly where every single one is. The books, the actual data, are stored in these big, fixed-sized chunks on a whole bunch of chunk servers. Those are your library shelves. And the most important part, the master is never in the data path. You don't have to go through the librarian to read the book. So the process is super efficient. Look, the client just makes one quick call to the master saying, "Hey, where's this piece of data?" The master replies with the locations, the client caches that info, and from that point on, all the heavy data transfer happens directly between the client and the chunk servers. This design is genius because it stops the master from ever becoming a traffic jam for the actual data. Of course, GFS was so successful that it inspired the open source community to build its own version, HDFS. You can see it was heavily modeled on GFS, but with some interesting differences. For example, HDFS defaults to a much larger block size, 128 megs. Why? Because it's tuned for the kinds of massive, sequential data reads you see in big data analytics jobs, like with MapReduce. Okay, so we've got our rock-solid foundation with the distributed file system. Now, engineers could finally build the superstructure on top of it, brand new kinds of databases designed from scratch to handle petabytes of data. And Google's answer to this was Bigtable. Now, you have to get this. This is not a relational database. It's a totally different way of thinking about data.
The paper itself famously described it as a sparse, distributed, persistent, multi-dimensional, sorted map. Yeah, that's a mouthful, but it hints at how different this beast was.
So what does that actually mean? The best way to picture it is as a giant key value store, but with a twist. The key isn't just a simple string. It's made of 3 parts: a row key, a column key, and a timestamp. And that timestamp part is the magic ingredient. It lets Bigtable store multiple versions of data in the exact same cell over time. You basically get a version history for your data for free.
Now, at about the same time, Amazon was tackling a slightly different but equally massive problem. For them, for things like their shopping cart, downtime was poison. Every second the service was down, they were losing money. So they built Dynamo with one single obsessive goal: make it always on. It had to be available no matter what.
And the way Dynamo achieved this always-on state was through some really clever design. It was completely decentralized. No master node to fail. Every node was a peer. Every node had the same job. This symmetry is what makes it so resilient. It could scale one machine at a time, and it even let developers tune the consistency level based on what their app needed. So here's the bottom line. You have 2 groundbreaking systems, both solving for huge scale, but they were optimized for different things. Bigtable was all about massive data storage and high-throughput analysis, perfect for indexing the entire web. Dynamo, on the other hand, was laser-focused on one thing: availability. It was built for services like that shopping cart that simply cannot fail.
And what's so cool is that these early systems did more than just solve their own problems. They actually defined a fundamental trade-off that every single distributed system designer has to wrestle with even today. Their legacy is what powers the modern cloud. And this is the trade-off, the big one. In a distributed system, you can't always have it all. You often have to choose: do you want strong consistency, meaning every single read gets the absolute most recent write? Or do you want high availability, meaning the system is always up and running, even if some of the data might be a tiny bit stale for a moment? Dynamo famously chose availability, and for a shopping cart, that makes perfect sense. It's better for a user to always be able to add an item, even if it takes a second for the back end to be perfectly in sync. But here's the thing. Building and running these systems, it was insanely complex. You needed a whole team of PhDs just to keep the lights on. So the real lasting legacy wasn't just the designs themselves. It was the idea of taking all that power, all that complexity, and hiding it behind a simple API, offering it as a managed service.
And that brings us to the final step in this whole evolution: Amazon DynamoDB. This is where it all came together. It took all the core ideas from the original Dynamo paper, that incredible scalability, the raw performance, the always-on availability, and wrapped it all up in a simple, managed cloud service. Suddenly, developers didn't have to worry about provisioning servers or managing replication. All that complexity just disappeared. You could just focus on building your app.
So, we'll leave you with this question, which gets right to the heart of it. For a service like a global shopping cart, what's more important to guarantee 100% of the time? That a user can always add an item to their cart, or that the cart's contents are instantly and perfectly consistent across every data center in the world? Because understanding these trade-offs, that's the key to building great applications today. It forces you to figure out what your system truly cannot live without.